And so last talk for the day is Scott Gaudi talking to us about Roman, which hopefully we can't wait to.
Can everyone hear me? Okay, I'm going to talk about the Roman Galactic Exoplanet Survey, and in particular the project infrastructure team. So I think most people are familiar with this, but in case you aren't, what is the Nancy Grace Roman Space Telescope? It was the #1 recommendation of the 2010 Decadal Survey for a large space mission. At the time, it was called WFIRST, the Wide Field Infrared Survey Telescope. Basically, this was a notional mission that took 3 inputs to the 2010 Decadal Survey. One was a dark energy mission called JDEM Omega, led by Neil Gehrels, the late Neil Gehrels. The second is the Microlensing Planet Finder, which was led by Dave. And the third was a near-infrared sky survey led by Dan Stern at JPL. The committee noticed that all 3 of these required very similar hardware, and so thought they could combine the 3 into one mission and get more science per buck. And so that was part of the motivation for them recommending WFIRST as the #1 space large space mission. As the Decadal Survey said, it should have 3 equal science areas. One is to probe dark energy using supernova, weak lensing, baryon acoustic oscillations, also galaxy redshift space distortions, a micro and exoplanet microlensing survey, and then also a GEO program, which nominally included a galactic plane survey. And these were, considered to be equal important components of the science that WFIRST could achieve. So that was the origin, and then since then it has evolved and become the Nancy Grace Roman Space Telescope. So who is Nancy Grace Roman? She served as NASA's first chief of astronomy throughout the 1970s. She's known as the mother of Hubble because of her instrumental work in making sure Hubble was developed and launched. And so she serves as a great inspiration for naming this mission. Okay, so what is Roman? It is basically the aperture size is very similar to the Hubble Space Telescope. The effective aperture is 2.28 meters when you account for the obscurations. The field of view is about 0.281 square degrees. That's made up of 18 H4RG detectors, and it's about a 300 megapixel camera. The wavelengths coverage is about 0.5 to 2 microns. The full width halfbacks at 1 micron. Diffraction limit is about 0.1 arc seconds. Pixel size is slightly larger than that. And the launch is, as I'll talk about, October 2026, and has a nominal 5-year lifetime, but obviously it is built to last a lot longer than that. So we can hope for at least a decade or longer operations with Roman. And the orbit will be at L2. And so it'll have 2 instruments. One is the wide field instrument I just mentioned. The second is a chronograph instrument. So when so there's a long history with WFIRST, but the current incarnation started from a telescope that was gifted to NASA, the 2.4 meter space qualified telescope. When that telescope was, NASA decided to use it for WFIRST, it was deemed that a chronograph could be tested on this aperture and try to show that you can do active coronagraphy in space. And that's important as a technology demonstrator for the Habitable Worlds Observatory, which was the #1 large space recommendation for the 2020 Decadal Survey, sort of. There are 5 core community surveys with Roman. For the WFI, there's a high latitude imaging survey, a high latitude spectroscopic survey, a supernova survey, the Galactic Bulge Time Domain survey, which is mainly what I'm going to be talking about, and very recently a galactic plane survey was defined. And these are going to take up roughly 75% of the prime mission lifetime. All of the extended mission lifetime will be GEO or general astrophysics time that people can propose for, including doing a follow-up microlensing survey if that's of interest. And that might be something we want to talk about during this meeting. Okay, so the wide field instrument has 7 filters, standard imaging filters, and then 1 wide filter, which is the filter that primarily is going to be used for the Galactic Bulge Time Domain survey. It has a bandpass of roughly 1 to 2 microns. And there's 2 dispersing elements as well, which may or may not be of interest to the Galactic Bulge Time Domain Survey, and I'll just leave that there. So the thing that makes Roman very exciting is that its field of view is large. So 0.281 square degrees doesn't seem large compared to, say, Rubin and LSST, but it's large for a space-based telescope. It's about 100 times the field of view of Hubble. But more importantly, maybe the mission is actually, the telescope is very efficient. And so it has about 1,000 times the sky mapping speed of Hubble. So that means you can you can map large areas of the sky relatively quickly, or in the case of what we're interested in doing, smaller areas of the sky at relatively rapid cadence. So you can look for time variable phenomena. So if you haven't been following Roman, Roman is real. This is showing the Goddard High Bay at Goddard Space Flight Center. You can see all of the major components of Roman are now in this high bay or nearby. They've all been delivered and they are now being assembled as we speak. So I'll show a little bit of this. I don't have time to show the whole thing, but you can go and look at these movies and it'll show you kind of what's going on. This is the Goddard High Bay and it just shows various activities that are happening in the process of building this mission. So this thing is very much real and very much coming very quickly. This is the wide field instrument after it was delivered, and you can see there's the instrument there, and they're lifting it off, and they're going to eventually put it. And they just recently inserted it into the instrument carrier. Okay, this is the kind of schedule. We are here. Where it says we are here near the end of fiscal calendar year 2024. Sorry, it should be over. So we're getting towards the end of the development of the mission itself. Phase E is the actual operations, and we are on track for an October 2026 launch date. I've shown this slide now, this exact slide, for about 2.5 or 3 years. So that tells you that the schedule has not slipped. And that's amazing, and that's fantastic. It's also terrifying, but there's a lot of work that needs to be done. But we are on time, on budget, with significant schedule reserves. So Roman is really going to happen, and it may very well be less than 2 years from today. Okay, so the Roman Galactic Bulge Time Domain Survey is one of these core community surveys. The notional parameters for this survey, and I stress notional because the actual survey design is being decided as we speak. And so within a few days, we will have what is likely to be close to, if not the final design for the survey. And if you want to ask me about it offline, I can tell you where it looks like we're going to be going. I will mention that there's a little bit more work that needs to be done because this is the notional design for this survey, but there's a larger committee that has to decide how the individual surveys work together, and that may change the actual survey design itself. So the results I'm going to be showing are for this notional design, which is 7 fields for roughly 2 square degrees. Again, most of the observations are taken in this wide filter. The cadence is 15 minutes, roughly 57-second exposures. Observations in other filters, the F087 and F213, which is roughly Z and K filters, every 6 hours. And then 6 62 to 72 day seasons. And exactly where we land on those two depends on how much time is devoted to this particular survey relative to the other surveys and the general astrophysics time. So for 72 days, it's about 41,000 exposures in this wide filter over the course of 432 days of the 5-year mission. And so this is a lot of data. This will be one of the longest exposures of the sky ever taken at these wavelengths. I won't say deepest because it's probably crowded limited. This, for that notional survey area, is an image created by Matthew Penny that is less than 1% of the total survey area. So you can see millions of stars here. There will be hundreds of millions of stars in the field of view of Roman. And that enables all sorts of science, which I have no time to go get into, other than microlensing. But obviously, it makes microlensing feasible because microlensing, as we know, is rare. But if you look at a lot of stars over and over again, then that rarity, then you start to get significant number of events at any given time. So NASA likes to set up science requirements, which basically says this is what we have to do in order for the survey to be a success. Dave and I and a bunch of people who worked in the previous incarnation of the project infrastructure team defined these survey requirements, and they're listed here. I will just highlight this one, which is of particular interest to this audience. Roman shall be capable of measuring the frequency of free-floating planetary mass objects in the galaxy from the mass of Mars to 10 Jupiter masses. And if there's one Earth mass free-floating planet per star, we measure this frequency to 25%. It's looking like this is probably going to be something that there's probably more than one free-floating Earth mass planet per star, based on the results we heard about earlier today. But if there is one, then we should be able to measure it at 25%. So this is part of where the yield of hundreds of free-floating planets comes from. Okay. So our survey was designed to meet those requirements, and all the surveys have to meet those requirements. So what do we expect from the survey? Simulating this is fairly involved. So you start off with a model of the galaxy that has the number density and kinematics and age of the stellar populations. Then you go and you simulate fields towards the galactic bulge. You choose your survey field locations. You cycle through those survey areas, those fields. You have some stars, you create images, you inject microlensing events into those images, then you inject planets into those, and then you find those planets, and that gives you your yield. So this is all work done mainly by Matthew Penny, but also some work done by Samson Johnson, and then a bunch of other people have started taking over from there. But I do want to highlight Matthew's work in this. It's been indispensable since the start of the kind of at least my part of the involvement in the Roman project. These are some simulated detections. One thing to highlight with microlensing, for those of you that aren't familiar with it, is this is a simulated detection on the left of a planet that has twice the mass of the moon. On the right, a free-floating planet with the mass of Mars. This is a 27 sigma and 23 sigma detection, respectively. These are not subtle signals. They are high signal to noise. They are unmistakable, and there's almost no astrophysical false positives that we know of. I would have said no, except for work done by this gentleman right in front of me that seems to indicate that maybe that's not true. Ask him about it during the break. But it may be that there are flare events that look like free-floating planets, which is interesting. Okay, so these are the yields with assuming some frequency of planets for bound planets, and then for free-floating Earths. Don't believe these numbers. If we knew these numbers, we wouldn't have to do the survey. But the point is the numbers are large, thousands, and free-floating planets could be thousands as well, depending on exactly which of these extrapolations that we heard about earlier today is correct. So the overall goal, of course, of this is to obtain a complete statistical census of exoplanets by combining with Kepler or the transits discovered with Roman itself, basically for planets with masses or radii greater than 2 times that of Earth, and separations from 0 all the way out to infinity, including the free-floating planets. And obviously, the free-floating planets, to the extent that they came from the bound planets, are telling us something about planet formation. And so that's, of course, a lot of what we'll be talking about during this meeting. This shows some more yields for the notional mission survey design I mentioned before. The left shows some simulated detections. Will look a lot like what we've seen earlier today. And again, these are very uncertain, but the point is the numbers are large. We should expect a lot of free-floating planets from this survey. This plot was already been shown. Don't really have time to go through it, but it basically shows the total mass of free-floating planets as a function of the mass of the free-floating planet. So if you have an equal number of mass per decade in mass, an equal total mass of free-floating planets per decade in mass, that would be a horizontal line on this plot. So the Sumi et al. Power law goes as mass to the -1, so that's an equal amount of mass per decade. total mass per decade. If that is actually correct, and it goes all the way down to say 10 to the minus 3 Earth masses, we will be able to detect things all the way down to the mass of Pluto with the Roman survey. At the upper end, we'll detect thousands. At the lower end, we'll still detect 100 or so. So the numbers are quite exciting. And then these are various theoretical interpretations, which I can talk about later if you want. Okay, so I just want to briefly mention the rest of my time, the Roman Project Infrastructure Team. So this is a NASA-funded team to help prepare the infrastructure for the Roman Galactic Bulge Time Domain Survey. I am the administrative PI. Dave here is the science PI. Our human infrastructure PI is Kevin Sassa, and we have a project manager, Chris Brandon. There's currently 71 members. That number might be 73 now since I haven't updated the slide. 12 working groups, including quite a few people in the room. Raise your hand if you're involved with yeah, so talk to these fine folk who are doing the actual work of this. So our goal is to ensure that our primary science objectives is achieved, and that's to complete the statistical census of planetary systems in the galaxy. We have a broader goal of building a large, vibrant, and diverse community of scientists and learners that can actually engage with the Roman mission. The important thing, one of the most important things about Roman, in my opinion, is that all the data will be immediately released. It's non-proprietary. So that means anyone with the proper tools can go and just harvest the science for themselves. Part of our job in the Roman pit, the project infrastructure team, is to develop those tools and to train the next generation of microlensers to be able to extract science from this data. And of course, we want to excite the public as well because they pay our tax dollars. So here's some of our activities. I don't have time to go into them. I just want to put them up here. So since we're going to post these slides, you can go through and look at them. And the point is that, and here's our working groups. We have 12 different working groups. I'm sure that will grow over time. I want to highlight this one, the Free Floating Planet Working Group, led by Will here in the front row. And if you're interested in being involved, knowing what this working group is doing and being involved in helping out with all the tasks that they have developed that are needed to be done before Roman launch and after Roman launches, talk to Will. And again, you can look at these slides when they're posted online. But the point is that we need help. There's not enough microlensers in the world to harvest all this data, and there's not enough of us even to train a lot of other people. So we need help. And so if you're interested in getting involved, and even if you don't know anything about microlensing, let us know. If you're not interested in getting involved, but just want to tell the world that microlensing is going to be great and is going to do all these great things, please do that so that we can get more people involved and get more people paying attention to what we hope to get out of this survey. So I'll just finish. It's an exciting time. I know I'm between you and eventually dinner. I want to emphasize Roman continues to stay on schedule and under budget with a launch anticipated in October of 2026. That's less than 2 years from now. There's a lot that needs to be done. We need your help. So those of us who have been in this field for a long time, some of us longer than others, some longer than others, longer than me. Roman represents the culmination and reward of many years of effort and sacrifice. So I want to thank those of you that have been in this field, microlensing field, for a long time and really came and developed the field. Thank you. This is, I think, many ways the fruition of all that work. And for those of you that are new to microlensing, I think this represents a fantastic opportunity, and I can't wait to see what happens. And with that, I will take questions. Thank you.
Yeah, so I wanted to emphasize Scott's point about help we need. We particularly need help from planet formation theorists who think that the microlensing survey will help us understand how planets form and eventually how determine how planets might be habitable and so forth. And in particular, one of the goals of this meeting is to spur some work to establish what we can learn from planets about the free floating planet observations. And in fact, while, Roman itself is approved, some additional observations would be very helpful for, understanding free floating planets better. And this is mainly the observations from other telescopes that can help to get these microlensing parallax observations and give us masses of some of the free floating planets.
Yeah, it's also worth noting that, after the 5-year prime mission is done, it may not, hopefully will not be the end of microlensing with Roman. We can imagine lots of extensions to this survey that, based on what we find in the prime's main survey, lots of extension that could probe different directions. But in particular, we could imagine doing a survey of a smaller subset of fields that would increase our sensitivity to lower mass planets and get us maybe even down below the mass of Pluto, depending on how good the photometry is. So those are the kinds of things that I want people to be actively thinking of.
Yeah, I want to ask a question about Pluto, which you just mentioned.
Yeah.
I'm doing solar system dynamics. It's pretty a consensus in the field that the solar system have ejected probably a few thousand Pluto-sized objects in the past. So given this number, let's say just a few thousand per star, what's the expect detection rate by Roman?
I think it's hundreds, but I have to go back and look at the yields. It's a lot.
Think.
Yeah. Yeah, I have to go back and look, but it's a significant number. One thing I do want to mention, sorry, I forgot to mention this before. There is a funding opportunity coming along, and I think, is this only, can anyone propose to this, or is only US people propose this?
Massive, yeah.
US people, okay. So anyway, US people can propose for an upcoming funding opportunity for wide field science teams to do work in support of preparing for the Roman Galactic Exoplanet, or the Roman surveys, core community surveys. So, and this could be theoretical work, for example. You want to propose some money to do some theoretical work to support that, just as an example. And so just, I can give you details if you're interested.
Yeah, I just had a comment on foreign participation. So to propose to NASA and get money, you have to be in the U.S. With a U.S. institution. But sort of, foreign people can collaborate, and if you're collaborating with someone on the Roman team to do work that's funded by another country, presumably, having collaborators with Roman, particularly if they get funded, will help you get funding in your own country. So, there's plenty of people that will be willing to collaborate on lots of things, that might qualify for funding. So, if you want to get support for a program and collaborate with someone, please let us know. People in the bid and maybe pursue.
Okay.
Scott, what is being done to provide for coordinated observations to get microlensing parallaxes?
Right. So I think so. A member of the pit, Wei Xinjiang, is involved with Earth 2.0, and we're working with him to try to coordinate some. Or they're interested in doing coordinated follow-up. Exactly how that's going to work politically, I think, is not clear. Part of the goal of this meeting is to talk to various people from OGLE, from MOAA, from KMTNet to try to coordinate those kinds of observations. There's a lot of work being done by, for example, Rachel Street and other Etienne Bachelet about using Rubin to do some coordinated follow-up. So I think you know, there are grassroots efforts to develop these kinds of contemporaneous observations. I think more is welcome.
It does seem that, well, we shouldn't let that just be an ad hoc thing. We have to really force that in order to get those masses, especially down at the lower end.
I agree. I think it's an important component of I think that science is going to be dramatically enhanced if we can get masses for even a fraction of the free-floating planets we detect. I think it's going to help everyone, and it's going to be much easier to interpret and all those kinds of things. So I agree that coordinated efforts are needed, and so part of the goal of let me know if I misspeak, Will. I think part of the goal of the Free-Floating Planets Working Group is to try to organize these kinds of efforts and to do it in a less grassroots, more top-down way.
That's exactly, that's one of our biggest pushes, is to Scott's point. I mean, mass measurements are really invaluable if you want to be able to do science with floating planets. You can try to marginalize over galactic models, et cetera, but without a mass measurement, it's really hard to pick out interesting features in the massive velocity distributions. And so what it means is that every single event for which we get a mass counts, right? It really does matter and can help with the science, which means that we want as much coverage as possible, as much redundancy as possible, and as many telescopes as possible. And we do want to make sure that it is as coordinated as possible so that, you know, we're trying to maximize the baseline. So one of my goals, not only for the working group, but also for this workshop, is to, get a lot of people in the room who all have affiliations with different telescopes and different observational ties, and maybe start trying to figure out how we want to plan for this, organize this. It's one of the reasons that every time someone talks to us and asks the question, so have you considered human observation? So that's a huge goal, and if you're interested or want to get involved, please do talk to